Today we're dealing with irrigation scheduling, in other words, how to determine the dates and amounts of irrigation during the season. This lecture is based on Chapter 20 of the book Principles of Agronomy for Sustainable Agriculture. To determine dates and amounts of irrigation, we will use the soil-water balance equation, which is shown here in terms of soil-water deficit. The soil-water deficit is the amount of water required to bring the soil back to fill capacity. And we apply this equation to calculate every day the soil-water deficit as a function of the previous soil-water deficit, dot of the previous day, by adding evapotranspiration and subtracting effective irrigation and effective rainfall. Apart from that, we will follow rules to decide the date and amount of irrigation using a parameter called critical soil-water deficit. Graphically, we can see the soil-water deficit variation starting just after irrigation. The soil-water deficit will be increasing, and the idea is that when we reach the value of the critical soil-water deficit, we need to apply irrigation to avoid exceeding that value. After irrigating, we should return the soil back to fill capacity, in other words, to soil-water deficit close to zero, as shown here. The critical soil-water deficit is the amount of water that the crop can extract from the soil without suffering water stress. Mathematically, it is calculated as the product of the effective rooting depth, the plant available water, and the allowable depletion. The units of critical soil-water deficit will be millimeters of water. The plant available water, in other words, the water retention capacity or water storage capacity, is the difference between soil water content at fill capacity and soil water content at permanent wilting point. For many soils with medium textures, the typical plant available water is around 120 millimeters per meter. If we need to remember typical values for sandy, loam, and clay soils, the plant available water would be around 150 for medium texture soils and 200 millimeters per meter for clay soils. Another factor to calculate critical soil water deficit is the rooting depth. The maximum rooting depth depends on soil conditions and irrigation management. In this table, we can see different values for the maximum root depth of different species with soils that are not limiting root growth. There is a wide variability among species, but also for any given species, the variation is important. For instance, for alfalfa, the rooting depth, the effective rooting depth maximum lies between 1 and 2 meters. This wide range of values is affected by irrigation management. Let's start by the idea that the irrigation management affects the distribution of the root system. In general, frequent irrigation promotes root growth in the surface layers, and long irrigation intervals favor more root growth in the deeper layers. This fact has led to many to believe that roots seek out water, which is not true. In fact, the mechanical resistance of the soil increases exponentially as the soil dries, so root growth occurs very slowly or does not occur at all in dry soil. When we start the growing season with a fully charged soil profile and we delay irrigation, the water uptake will be drying the soil progressively downwards. For any time, the best conditions for root growth will be on the wet layer just below the dry front. So if the irrigation interval is long enough, we will be favoring root growth in the deeper layers. To calculate the effective rooting depth for an annual crop, we can use this equation where rooting depth is equal to its minimum value plus the difference between the maximum and minimum value multiplied by a root factor. This root factor is equal to time over the time from sowing to the maximum rooting depth, or we can alternatively use a rooting factor based on thermal time. In other words, the ratio between thermal time at a given time and thermal time from sowing to the maximum value of root depth. For instance, let's consider a maize root growth, the maize root growth when the crop has a cycle with 30, 40, 50, 30, according to the crop coefficient curves of FAO. The maximum root depth is 1.35, which is the mean value obtained in table 20.1, and the sowing depth is 0.03. In principle, the time from sowing to maximum root depth is equal to the time until the maximum crop coefficient. In other words, it would be the sum of the durations of the first and the second stages of the crop cycle. In other words, in this case would be 70 days until the maximum rooting depth is obtained. Then, substituting in the equation, the rooting depth would be calculated as the sum of the minimum value plus the difference between the maximum and the minimum value multiplied by time over 70. Here we see an example of the root concentration below an almond orchard in Cordoba, and here we see the edge of the wet bulbs. This is an almond orchard irrigated using drip irrigation, and we see that the roots are concentrated in the areas wetted by the drippers. This is the same for an intensive olive orchard, and the root depth goes down to a compacted layer around 60-70 centimeters depth. The third factor to calculate the critical soil water deficit is the allowable depletion. That is the fraction of plant available water that can be used safely. In other words, the fraction of plant available water that can be extracted by the soil without entering into water stress. For extensive crops, when expansion is not needed anymore, we can use a general value for allowable depletion between 0.7 and 0.8. In other words, 2/3. For horticultural crops, or when expansion is critical, we should use much lower values. And we can use this equation here that calculates the allowable depletion as a function of ETO. This equation implies that the allowable depletion decreases as the reference evapotranspiration increases, depending on a factor that captures the sensitivity of the crop to water stress. In the same table, in table 20.1, the factor for calculating the allowable depletion is also shown. The largest values, for instance for rice, 0.16, mean that the crop is more sensitive to water stress, and the lower values, for instance 0.07 for cotton or for palm trees, means that the crop is less sensitive to water stress. For example, we will calculate the critical soil water deficit for an onion crop on a sandy loam soil of 1 meter depth. The expected maximum reference evapotranspiration is 5 millimeters per day, and we assume plant available water of 120 millimeters per meter. In Appendix 10.3 of Chapter 10, we find that for onion the maximum rooting depth lies between 0.5 and 0.8 meters. We take the mean value of that interval, in other words, 0.65 meters. In the same table, we can also find that the factor FAD for onion is 0.14. Therefore, we apply the equation for calculating AD as 1 minus FAD multiplied by ETO, 1 minus 0.14 multiplied by 5, which leads to 0.3 for AD. Now we apply the equation to calculate the critical soil water deficit as the product of the rooting depth, plant available water, and allowable depletion. Rooting depth is 0.65, plant available water is 120, and AD, allowable depletion, is 0.3, which gives us 23.4. For a maize crop after full cover on a sandy loam soil of 1 meter depth, we will calculate also the critical soil water deficit. Now the expected maximum ETO is 8 millimeters per day in July, and we assume also plant available water of 120 millimeters per meter. In table 20.1, we find that for maize, the maximum rooting depth lies between 1 and 1.7 meters. In this case, we will take 1 meter. Why? Because the soil is already limiting root growth. So, if the soil depth is 1 meter, the maximum rooting depth will be 1 meter. As we are dealing with an extensive crop and after full cover we are not concerned about expansion, we can adopt an allowable depletion of 0.7. Therefore, the critical soil water deficit will be the product of the rooting depth, 1 meter, plant available water, 120 millimeters per meter, and AD 0.70, which gives us 84 millimeters. We have already explained how to calculate the critical soil water deficit. Now let's see what are the decision rules for deciding on the dates and amounts of irrigation. To calculate the dates of irrigation, the basic decision rule is irrigating when the soil water deficit equals the critical soil water deficit. If we irrigate sooner than that, we will increase the number of irrigations, and if we irrigate later than that, we will incur in water stress. Increasing the number of irrigations might imply a higher cost for irrigating, but that depends on the irrigation system that we have. After we have decided to irrigate, after we have decided the date of irrigation, the basic rule would be applying a depth equal to the soil water deficit at that time. That would bring the soil back to fill capacity, in other words, to deficit zero. If we apply a larger depth, we will be applying excess water and therefore we would have percolation. If we apply a smaller depth, we would not be refilling the soil. This might be an interesting alternative for some situations as we will see later. We can calculate the dates of irrigations according to the soil water deficit and the critical soil water deficit. But sometimes we have restrictions to the dates when we can irrigate. For instance, it is very common that in the irrigation system the water is delivered to the farmers on a fixed rotation. In other words, the farmer has water every week one day every week or 1 day every 10 days, etc. Holidays may also be restricting dates of irrigation. But more important, other operations in the farm, like the application of pesticides, of preparation the soil for harvest, and well, in that case we prepare the soil or the crop for harvest, or we may need to do some tillage. Apart from restrictions to the days, we might be restricted to the irrigation depth. But the flexibility of the irrigation system to apply more or less irrigation depends on the irrigation method. The lowest flexibility is that of surface irrigation, which usually is designed to apply huge amounts of water, above, let's say, 80 millimeters per irrigation. The sprinkler systems have medium flexibility, and we can apply amounts as low as 10 millimeters in one irrigation up to more than 100. The highest flexibility is that of drip irrigation, where we can apply amounts as low as below 1 millimeter per irrigation. In this graph, we show the water balance throughout the growing season for a sorghum crop grown in Hinojosa, sown on April the 15th, and we are following the basic strategy, which means applying irrigation when the soil water deficit equals to critical soil water deficit, and applying an amount equal to the soil water deficit at that moment. In the graph, we see that the critical soil water deficit, the red line, increases until it becomes constant when the maximum rooting depth is achieved. The green line varies following changes in evapotranspiration and rainfall. The blue lines indicate irrigation. In this case, we have had 4 irrigations. But look that the last irrigation here has been reduced as compared to the other irrigation events. And that allows that the final soil water deficit goes below the critical soil water deficit. That is done, or that is corrected, to let the soil as dry as possible at the end of the growing season. We will discuss that later. Here we consider a so-called safe strategy that implies irrigating when the soil water deficit is equal to the critical soil water deficit minus 20 millimeters, and then we apply an amount equal to the soil water deficit. What we are doing here is that we are not using all the storage capacity of the soil. That means that if we have any problem with the irrigation system, we have time to fix the problem before going into water stress. In this strategy for rainfall capture, we are irrigating when the soil water deficit reaches the critical soil water deficit, but we are not returning the soil to fill capacity. In this case, we are applying amounts equal to soil water deficit minus 20. That means that there is still water deficit in the soil after irrigating. In other words, we could use, or we could store rainfall arriving during the growing season. In this strategy, we are dealing with a fixed rotation of 10 days. In this case, the rule is to irrigate when the soil water deficit for the next possible irrigation date exceeds the critical soil water deficit, and in that case we apply an amount equal to the soil water deficit. Look that even if we have water every 10 days, we not need to apply water every 10 days. See that on day 40 we would have water for irrigating, but we do not apply irrigation. Why? Because we can wait until day 50. Example: we are irrigating corn during summer with mean daily values of ET of 8 millimeters per day. Water is available every 10 days. In other words, on 1 July, 11th July, 21st of July, etc. The critical saltwater deficit is 120 millimeters. And on July the 1st, the saltwater deficit is 20 millimeters. We have water on July the 1st. The question is, should we irrigate? And the answer is no. Why? Because we can wait until July the 11th. Here we calculate the saltwater deficit on July 11th as the initial value, 20, plus 10 days multiplied by 8 millimeters per day. And that gives 100 millimeters. That is below the critical saltwater deficit. In other words, we can wait until July 11th, but we cannot wait until July the 21st. We calculate the saltwater deficit for July 21st as the initial value, 20 plus 20 days multiplied by 8 millimeters per day. That gives 180 millimeters, which exceeds clearly the critical saltwater deficit. In other words, in summary, we should irrigate on July the 11th with 100 millimeters of water. We saw before that the irrigation schedules that we have shown for sorghum are corrected in the last irrigation. This is intended to leave the soil as dry as possible at the end of the growing season. And for that, we could use, at the end of the growing season, an allowable depletion of 0.8 to 0.9. In other words, we would be using 80 to 90% of the plant available water. With this strategy, we would allow winter storage of water by rainfall. And in that way, we would also be avoiding drainage and nitrogen leaching during the winter. To calculate the amount of irrigation for the last irrigation, we apply this equation, where the amount of irrigation is equal to the soil water deficit at the time of the last irrigation minus the soil water deficit at the time of harvest plus the total evapotranspiration from the last irrigation and harvest. For instance, we are irrigating following the rule that we apply irrigation whenever the soil water deficit is equal to a critical soil water deficit of 96 millimeters. This comes from a soil depth of 1 meter, plant available water of 160, and allowable depletion of 0.6. We want to irrigate on September the 1st and want to end the season on October the 1st with allowable depletion of 0.9. The final soil water deficit should be therefore 0.9 multiplied by 160 multiplied by 1, that gives 144 millimeters. The evapotranspiration during September is 3 millimeters per day on average. We apply the equation where the amount of irrigation to apply is equal to the soil water deficit at the time of the last irrigation minus the soil water deficit at the time of harvest, 144, plus the total evapotranspiration during that period, which is 30 days multiplied by 3 millimeters per day, and that gives us 42 millimeters. In other words, on September the 1st, instead of applying 96 millimeters and bring the soil back to fill capacity, we would apply only 42 millimeters, which would lead to a very dry soil at the end of the growing season. These ideas for calculating dates and amounts of irrigation based on the water balance led to the development of the so-called mean irrigation schedules, which could be applied to dry areas with little rainfall and were proposed by Fereres and colleagues in 1981 published in California Agriculture. Here we see a graphical curve to calculate the dates and amounts of irrigation. What they did was to plot the cumulative evapotranspiration versus time and put on the y-axis the amounts of saltwater deficit corresponding to the critical saltwater deficit. And now, going from this curve down to the x-axis, we would find the dates of irrigation. With that, we would calculate the dates and amounts of irrigation for the whole growing season, which is very useful for planning the irrigation season. But this is only applicable to areas where rainfall is negligible during the irrigation season. In the case of high-frequency irrigation, for instance using drip irrigation, we can ignore the soil storage and merely apply, using the irrigation system, the amount of water lost by evapotranspiration. For instance, let's consider a tomato crop with a crop coefficient of 1.2, irrigated with a drip system with emitters of 2 liters per hour spaced at 1 by 0.75 meters. The application rate is obtained by dividing the discharge rate of 2 liters per hour over the area covered by each dripper, in this case 0.75 square meters. And that gives us an application rate of 2.67 millimeters per hour. Yesterday we had an ETO of 7 millimeters per day. Therefore, we can calculate the crop ET multiplying the crop coefficient 1.2 by ETO of 7, and that gives us 8.4 millimeters per day. Therefore, today we should apply an irrigation with a total duration of 8.4 divided by 2.67, and that gives us 3.15 hours per day for the irrigation duration.